Let's take a look at differential equations and power series. Differential equations are where we're given a formula for the derivative, or we make up a formula for the derivative based on how we know the physics or the biology of the system works, or chemistry, I suppose, or even psychology, or math, or statistics, all kinds of fun stuff. So we have a formula for the derivative, and then we want to find a formula for the original function, which sounds like just integration. But usually the derivative formula involves the original unknown function, and so we can't just take the integral because to get the integral of f prime here, we'd have to take the integral of f divided by x, but we don't know what f is in the first place. That's why we're trying to take the integral of f prime. So there's a few different ways to do it. You can take a whole course or 2 or 3 in differential equations. We can talk about it some other time. If you're interested, send me email. But for now, let's take a simple approach and just guess an answer and then check it. So let's guess and check. And there's hardly any intuition we can use here. Let's just use plain old, how about x squared? So let's say f of x equals x squared. You might end up seeing that I'm a very good guesser on that. So let's check it. So that's my guess. Let's check it. What's f prime? That would be 2x. So that's one side of it. The other way to check it, or the other thing we need to do, is check what is 2 times f of x over x. That would be 2 times, and I'm going to put in my guess here, x squared over x, which is 2 times x, because the x squared, the squared gets canceled with the x. So I got the same thing on both sides, and so my guess checked out. The differential equation said that these two things had to be equal. I calculated them and they were equal, so x squared satisfies the differential equation. So next we'll try a much more interesting and involved one. You might remember somewhere seeing that if you have a spring, so for a differential equation application, let's look at the idea of a mass either hanging from a spring and kind of bouncing like this, or compressing a spring if it's in like a car suspension or something, where you've got the tire and then a spring for the shock absorber assembly, and then the weight of the car pressing down on it. And the relationship between how compressed or stretched the spring is and how much force it applies is basically, to a first order approximation, we could say, for Taylor polynomials, it's just some constant times how stretched out or compressed the spring is. Except if you squish the spring, the force should push in the opposite direction, so we'd have a times -1 here. And then we have to remember that force is mass times acceleration. And acceleration is like f double prime of t. Actually, so we should say t here. So the force is k times the displacement, the amount of stretch of the spring, times -1. So our differential equation is f double prime of t equals, now I'm going to just pretend k is equal to 1 because it makes life a lot easier for now. So we'll have a 1 there and a -1 there, so we'll have negative f of t. So we're saying that basically the acceleration is the negative of how stretched out or compressed the spring is. So we're saying let's use k equals 1 for simplicity. So we want to solve that differential equation. This thing is called a simple harmonic oscillator. We're pretty sure this thing will just kind of sit there and bounce, maybe like a sine wave, so maybe we'll try a sine wave. Another way to say this is that f double prime of t, if I add this to both sides, plus f of t equals 0. And another way to say 0 is 0 plus 0x plus 0x squared plus 0x cubed plus dot dot dot, right? So if we're doing power series stuff, if I do this, I should get a power series that is all zeros. So let's say we're going to try sine of x, which we know is the sum n equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So we could do all of our operations on that general form, but it's nice to do stuff a little more concretely to begin with. So let's say here's, or we could use a t here. We'll just keep using an x, that's fine. So what is f? It's the sum for sine, so it's 0 plus 1x plus 0 plus negative 1/3, 1 over 3 factorial x cubed plus 0 plus 1 over 5 factorial x to the 5th. And we're going to need a lot of room here, and we're going to try to keep things in nice neat columns. Plus 0 plus 1 over 7 factorial x to the 7th. That should be negative. So that's my f. We're saying that this is our original function, or this is our displacement function, and we're hoping or guessing that it solves this. And then let's take the derivative. So what's f prime? Derivative of 0 is 0. Derivative of 1x is just 1. Plus a 0 there. We'll skip that part. Plus negative 1. What's the derivative of x cubed? It's 3x squared. So we'll say x squared times 3, and we have a 1 over 3 factorial here. What's going to happen with the 3 and the 3 factorial? 3 factorial is 3 times 2 times 1. One of those 3's is going to cancel the 3 here. So we'll just get a negative 1x squared over 2 factorial. And then plus 0. Here we'll get 1 over 5 factorial, 5x to the 4th. Here we'll get negative 1 over 7 factorial, 7x to the 6th, plus dot dot dot. And then we can simplify this part. So we have a 1 there. We have 1 over 4 factorial x to the 4th. We have 1 over 6 factorial x to the 6th, negative there, which we recognize as cosine, right? 1 minus x squared over 2 plus x to the 4th over 4 factorial. Not a surprise there. And now let's take the derivative again, because we know we need to check the second derivative there. So let's take the derivative again. The derivative of 1 is 0. The derivative of this will be negative 1 over 2 factorial 2x to the 1. Derivative of this will be 1 over 4 factorial 4x cubed. Derivative of this will be negative 1 over 6 factorial 6x to the 5th. And then simplify that to get negative 1, 2 divided by 2 factorial is just 1 factorial. X to the 1. 4 over 4 factorial is 3 factorial. And then negative 1, 6 over 6 factorial is 5 factorial. Like that. And now let's go back and check. Is f double prime plus f equal to 0 plus 0x plus 0x squared plus 0x cubed plus 0x to the 4th plus dot dot dot? Well, let's look back at what we have. We have the little f, our original function that we guessed. We have the f double prime, and let's think about what would happen if we add this row to that row. Well, here I have a positive 1x, and here I have a negative 1x. So those will cancel. Here I have a negative x cubed over 3 factorial. Here I have a positive x cubed over 3 factorial. So those will cancel. Same pattern here. I have a positive x to the 5th over 5 factorial. I have a negative x to the 5th over 5 factorial. That'll cancel. So it certainly looks like everything will cancel, and it does. You might say, well, where's this going to cancel? Well, there should have been another term over here because this goes on to infinity, right? So when we take the sum out to infinity, all the terms cancel. So our guess of f of x works. It satisfies f double prime plus f equals 0. So in some problems, I mean, here I just kind of guessed because I knew that this is a harmonic oscillator and sine should work okay for that. But sometimes instead of a guess, the task is more like, here's a differential equation, and then the book tells us a guess for the solution, and it's up to us to check it, but we don't actually have to use any intuition or anything to come up with a guess. The book just says, hey, here's a function, try this as a solution, and you just have to show that it satisfies the differential equation.